we will start with the session that is about experimental mechanics, session 2, and I would like to all speakers to thank the presence, and the first wall of all of them is Sirico, that we will talk about mechanical characterization of different biochar-based cement composites. Sirico, are you there?
Yes.
Hola. Yes, Sirica.
Present.
Hello. Nice to see you. A pleasure to meet you, and welcome to the conference. And thank you by your presentation about the talk, mechanical characterization of different biochar-based cement composites. Is a very interesting work. Thank you one more time. And basically, in 1 minute, what you can summarize about your work?
Thank you very much. And my work is about an experimental investigation on the properties of different cement composites with the addition of biochar. Biochar is the byproduct derived from a thermochemical conversion in order to obtain syngas. So biochar is the byproduct of this process. And biochar is now used as in the agriculture field, but it has a lot of properties, so it can also be used as additive in cementitious composite. And this is research that is nowadays very important in order to obtain concretes or cementitious material that are sustainable, so environmentally friendly. So in our research, we have done 3-point bending test on cement paste at the University of Torino and on mortars at the University of Parma in order to investigate if biochar can be used as additive in cementitious material. And the results was quite satisfactory. Biochar does not increase so much flexural strength and fracture energy, but the results are not so negative. So they are promising. From an environmental point of view, because we insert this waste, and there are no economic disadvantage, because usually biochar is disposed as waste. So we can insert biochar in mortar and in cement paste. And also from an environmental point of view, because biochar can incorporate carbon in a stable form in its structure, so civil structure can become storage of carbon.
Okay.
Because carbon is not released in atmosphere, but it is locked for decades in the structures.
Okay, basically 2 questions.
Yes.
One of them is more in general context, and the other one is more technical. In terms of general context, my question is, you used virgin wood, correct?
Yes, there is of local forest. So there are virgin wood chip, but there are waste from local forest.
Waste from the local. But
From
my
local
question,
forest, waste from local
okay,
forest, yes.
okay.
Wood,
Uh,
food source.
Yes, yes, okay. Is natural wood, but waste of the forest. My
Yes, yes.
question is, if you use um, previous burned wood, have you the same benefits? For example, in a forest, after fire, you have some woods burned. Do you think that you can use that?
Um, yes, I think that
In
there's
terms of chemical composition, do you think that have any alterations in terms of the final experimental tests?
yes, of course. If the chemical composition is different, the cement composite are a lot affected for this. So I think that burst wood could be used, but it is necessary an experimental investigation. Before doing it, I think it is impossible to predict the results because also using the same wood chip but different thermochemical conversion, for example, pyrolysis instead of gasification, the results are quite different. So I think that it could be possible, but the results, I don't know.
Yes, probably you understand my question because unfortunately nowadays you have a lot of fires in forests, and could be one solutions to solve all problems with these woods, burned woods. Probably could be interesting solutions for applications. This is or this was my context of my question.
Yes, yes.
Okay, to understand the context, and there are any. Do you think that is a possibility to to go along this way to use waste but burn it after a fire? Could be a solution for
Yes,
your for,
yes, I think it could be possible, but I don't know if the result would be promising. I don't know because changing the biomass, the incoming biomass in the process would result in very different results. So I think that it could be possible, but if the results are good or not, this I don't know.
okay. Other question more in terms of technical point of view. You use nano and micro particles, correct?
Yes.
Uh, did you do any optimization of the size of the particles, or you just use it from the char? Did you select, for example, 10% of this galvanometry, 20% of other galvanometry, in order to have the best size optimization?
No, biochar was sieved. Yes, in the sieved, yes, because the biochar with a higher grain size, so not nano and microparticle, is used in the agriculture field, while the nano and microparticle are too small for the agriculture field, and so this part is used in our experimentation because it would be interesting to use also this part of biochar that nowadays is not used in another field.
Yes, yes, but you you use it, the
Yes,
biochar that you receive, but you
yes,
don't control the amount of different galvanometry in the concrete. You
no,
put directly as you received.
yes, yes, exactly. Yes,
Do you think that if you optimize the galvanometry in order to decrease the voids between grains could be could be a solution to improve the results that you have?
yes, I think that it could be possible even if the granulometry was all under 40 nanometers and 50% under 8 nanometer. But I think that an optimization could be an interesting step to do, yes.
Okay, this is, for example, one of my suggestion. For example,
Yes.
to optimize the galvanometry, to use a model to know how much is the percentage of the size in each range. Could be
Okay.
interesting in order to decrease the amount of concrete or including the voids
Yes.
would be one
Yes.
solution. Okay,
Yes. I think is
thank you very
thank you.
much. Any question, please, from the audience? There are any question is welcome. No questions? Okay, thank you very much. I wish the best for your work and for promising results that you will have. Thank you very much, Sirico. Bye bye. Okay, thank you very much. And the next talk is about Bento.
Hi, Professor. Hi, everyone.
Hello, how are you, Bento? Everything okay?
Fine.
You
You?
you you will talk about the self-sensitive FES welded bonded joints for structural monitoring, correct?
Correct.
Okay, nice. And I would like to start with the same question. In very few seconds, please summarize your work, please.
So, for the past year, we've been working in ways to improve the friction stir welding process. To do that, we initially combined with adhesive, forming hybrid joints, which displayed better tensile and fatigue performances. But we observed that when comparing to riveting or other joining techniques, there were still some drawbacks, one of which was the impossibility to monitor the integrity of the joint during its manufacturing and service life. So in this paper, we tried to incorporate Bragg sensors so that we can monitor joints performance in those moments and benchmark the results against finite element models to validate the fibers readings.
Okay, thank you very much. And I have one question is about, I don't understand, sorry, but I don't understand very well how you put, where you put the sensors and the capacity that they have to monitorize a welded joint. Please, in your paper, I saw the figure, but it's not completely.
Which one? Don't mind me asking.
I'm trying to obtain here. I have your paper open, but where you put the brake sensors, please?
So we need to put brake sensors in parallel with the weld line so that the weld tool doesn't cross the sensor and doesn't break it. So we machine a channel and the brake sensor, a very small channel, and the brake sensor goes inside of it before the welding process.
Before, yeah.
Then we weld in parallel to the sensor.
Okay, and you use the brake sensor in this region that you did perform the valley, and you glue. Use an adhesive joint, correct?
Yeah, the adhesive joint is put there before the welding process as well.
Okay, and is one around it, correct?
Around it, yeah, one around it.
Yes, and the problem is the temperature that you use yes, is an Araldit 420. And the temperature that you are using during the welding don't affect this.
No, that was a problem that we asked ourselves a few months back, and we checked. I'm not sure right now, I don't have the data, but the limit is like 100 degrees below, so it shouldn't affect the quality of the
because this resin, this heralded resin has a TG around 60, 62 degrees, and when you are welding, your temperature is higher. And you don't have problems with this temperature. Is not affecting the
we asked ourselves
the adhesive.
It might affect a little bit, but the results are in hybrid joints with FSW plus adhesive are still better than only FSW, so it's worth it, even if it does affect a little bit.
Because my question is, okay, you are trying to have a technique to monitorize the joint, and I am talking about the adhesive, but there are a relation between what you want and what I am talking, because if you change the resin, you don't have effects on the final results that you will obtain.
I didn't understand the question. You asked me if if it was another another glue, the result would be different.
Yes, because you can have possibility to have a structural change in terms of the glue, and this change of the glue don't affect the final results.
Yes, it does affect, and it also affects the tensile results and the fatigue results and the Bragg readings as well. It affects everything. But
how you can obtain consistent results if the glue can be affected by temperature?
We machine like 3 of these specimens presented, and they all presented similar results. So if we keep the glue constant and the materials constant, the results will be constant as well.
Okay, you should guarantee that all procedure is the same in order to have.
Yes.
Okay, and for example, and if during the operational life, if the material is affected by temperature, the resin could be changed again in terms of chemical aspects. In this case, you don't have different results during the operation life.
Yes, you have different results if the glue is compromised. But the thing is, because we have the Bragg sensor, we will be able to detect that the glue was compromised.
Okay. You can obtain a relation in order to.
Yeah, that's one of the purpose of the sensor, is to tell us that the process was compromised. It's not as good as it should be. It's deforming more than it should be. There are cracks appearing. It can tell us many things.
Yes, but not only during the welding process.
No, not only. It
Also
keeps on. Yeah.
only
During service
after
life, it works.
during in service life.
Yeah,
And
it works in both moments.
And I was talking this effect in terms of in service life. These
Yes.
effects of different alterations in terms of characteristics of the adhesive.
Yeah, the Bragg sensors indicates us that the adhesive is behaving differently, that the deformation in that area is higher or lower. It tells us that.
Okay, this technique can be applied to real contests. Is promising for real applications. What you should develop, what you should improve in order to apply in a real in-service life.
Mm-hmm. So I think we should develop a standard process. Like the first step is what I think is what we develop in this paper, which was the creation of the process. Like we need.
Yes, this is the first step. This is your first step.
Because in the first tries we didn't machine that channel, and the fibers kept on breaking. So that's one big detail that we observed it was necessary. And there should be others depending on the geometry in which this technique would be applied. But I think that this is a good first step to achieve that.
Okay, for first step, you are optimistic.
Yeah, I think so.
With the results.
Yes.
Okay, thank you very much.
Thank you.
Any questions, please? There are any questions to Bento? Okay, if not, thank you very much, Bento. And
thank you, Professor.
I wish the best, Lucky, for your second step in your work.
Thank you. Thank you very much.
Bye.
Bye.
Okay. Good afternoon. And
good afternoon.
The next is Paul Ziani, correct? About
yes,
structural.
But I am Carlo Bruti, other author.
Okay,
there is a change.
Okay.
There is a change.
Okay,
I am not so problem. Young as the other authors.
No problem.
No problem. Thank you.
Here the age is not a problem. and welcome, and we thank by your presence here, and congratulations by your work about structural integrity assessment of pressure equipment by acoustic emission and data factor analysis. Okay. Please summarize your work in a very...
Yes, I do. And our work is about the problem to assess the remaining life of buried tank without lifting from the earth. And so there is now a procedure based on acoustical emission that is a property of the INAIL, that is the Institute of Italy for the safety and health during work. But the main aim of scope of our work is to assess if it is possible to obtain the same results of the well-stated procedure by another technique of analysis of acoustical emission. This technique of analysis is based on fractal dimension and using the box counting method. there is a method available in bibliography, well stated, well supported by experimental data. And we applied this method to verify if during the pressurization of three tanks of the same type with different damaging process, the results were in agreement with those obtained with the inhaled procedure. And fortunately, we get the same result. The analysis by fractal of the acoustical emission signals, we used also for assess the fatigue damaging process, with also in this case with good results.
Okay. You say that in this moment this technique has some limitations yet,
but in sense that now it is a qualitative tool to verify the integrity of the structure of because there are few experimental data regarding the same type of structure under the same type of stress state to transform this technique in a quantitative. In few words, when we measure the fractal dimension, we can see that if there is a damaging process, the fractal dimension suddenly decreases. But this is the only information available now, because we don't know when the fractal dimension show that the damaging process is near the collapse. There is a lack of information about this, and so also the theoretical approach about the connection between the fractal dimension and, for example, the distance of a crack from the critical condition, there is a crack of information about this and lack of information about this, and for now it is not possible to convert in a quantitative method. But I hope that developing more work about this, it is possible to get this result.
Okay. Basically, what is the main advantage with the fractal analysis? Compared with the traditional acoustic emission, what you can obtain, which benefits you obtain with this technique compared with the...
Okay, if you compare with the other procedure available, the main advantage is that the other procedure are based on algorithms that are in property of the society that developed this. And instead, the fractal analysis is a well-stated tool available in reference that is for everybody, and so there is possible to use in research laboratory and also in industrial check without obtain a license from the other society that possess the procedure.
Okay, you think that you can obtain benefits in terms of time or in terms of...
Yes, because the elaboration to get the result is less complicated. It's more complicated to explain, but it is less complicated to do. And so it is possible to automate to make develop an automatical procedure on time. And so during the test, it is possible to obtain these results. Now in the world there are developing many procedures based on acoustical emission to obtain the knowledge reliable about the damaging process of structure. For example, in Japan, there are rules that allow to check the bridges after an earthquake. I think that by means of fractal analysis, it is possible to improve this procedure, because in few words, the process of breaking material is a process in which we are many damaging processes distributed in the volume of the material. But when we approach to the collapse, one zone of damaging has an acoustical emission higher than the others. This means that the acoustical signals are more ordered, and the fractal dimension measure the order of emission. And so this means that can be applied to each type, all type of materials and type of structures, theoretically. But experimentally, it is necessary to improve this technique.
Okay. Any questions from the audience, please? There are any questions? Okay, if not, thank you very much by your interesting word, and I wish the best for your progress in this technique and this work. Thank you very much.
Thank you very much for you. Bye-bye.
Bye. Okay. We will go to the next speaker, that is Cruz from
Hello.
Portugal. Hello, good afternoon, Cruz. How are you? Everything okay?
Good afternoon. Yeah,
Okay.
and you?
Thank you very much and welcome to the conference. Cruz, you will apply a talk about development of a mini tensile approach for sheet metal testing using digital image correlation. Okay?
Yes.
Please, in few seconds, summarize your work.
Okay, good afternoon, everyone. The main objective of this work was to develop a mini tensile equipment to perform tensile and compression tests on mini size specimens using digital image correlation.
Okay, my first question is related with size. Okay, in terms of project, in terms of design, we know that the size of the sample has some effect on the results that we will obtain. How you explain in this context your solution?
Sorry, I don't understand.
In terms of projects, in terms of design conception, the size of the samples has effect on the results that we have, and how you can what you can say in this context about your small size of your samples?
Yeah, we choose a small specimen size because we needed to perform compression tests, and with a macro scale, for example, a dog bone specimen, usually used in tensile tests, we can't achieve compression strains for a higher value of strain. So we use we reduce the scale of the specimen, and the objective, the most important objective was to try to compress these specimens without the buckling phenomena.
Okay, but you are reducing the buckling
Yeah.
phenomena, but you are increasing other phenomena. For example,
Yeah.
you are reducing the probability to obtain defects on the sample.
Yeah, of course. Yeah,
Correct? And
yeah,
how in this context you can compromise the buckling effect with, for example, other effects, including the defects in the samples?
one of the most there is a lot of variants that we can improve. One of them is the machining process that we use the milling process that the uniform area of the gauge area was not so uniform. So we have some problems on that aspect, and we try to, as a future work, use some more efficient process like ADM process to improve these defects and obtain better properties and better results compared with the macro scale.
Okay, okay. And what you can say when the micro is compared with macro scale in terms of stress strain fields? When you decrease the size of the sample,
yeah, we don't have
the stress and strain fields change.
Yeah.
Is a significant change?
We didn't have a lot of difference in preliminary tensile tests. The most difference that we observed was in the total elongation that the specimen can reach. That is significantly more higher in mini tensile specimens. But
Okay,
the stress distribution, the strain distribution is almost uniform in the gauge area, like in a macro tensile test.
Okay, you can say that this is you have promising results.
Yeah. Yes.
And in terms of costs, is significantly what you are suggesting.
Sorry, in terms of
money to produce the samples
money.
and time.
Yeah,
the cost of production of and including the equipment is much more cheaper. Your solution.
With mini tensile specimens, we use much less material. So in material, we can use less material and less cost. But in the total cost, I think because we need more efficient process like EDM that have more cost than milling, for example.
Oh, okay. Thank you very much.
Okay.
Please, any question for the audience to Cruz? There
Sure,
are
I have a
any,
question. Sure, I
please.
have a question. Can you hear me?
Yes, we are listening to you. Please, please.
Um, Daniel, excellent presentation. Thank you for your work. You
Thank
mentioned
you.
in one of the comments here that your objective was to obtain a very uniform strain field. My question is, in the tension compression test that you've shown, I'm unsure of the direction. I think you took the samples from one of the in-plane directions in the sheet.
Okay.
But my question is, it looks like in the reverse yielding process in the compressive, or in the after the compressive reversal, it looks like there's some inhomogeneity or some
Yeah.
non-uniformity in the strain field.
Yeah.
Is that, how are you measuring the strain? Is it the average of the whole field, or is it a local area that is reverse yielding differently than the surrounding material?
What you're saying is true. In compression tests, tension and compression tests, we have different results in tension and compression. In tension, we have a more uniform distribution, but in compression, there are a difference between the lengths of the specimens. We use a virtual extensometer in the center of with the same length of the gate's length. I just want to say that the main objective was for develop a new equipment for trying to test compression tests. And there are a lot of work to do to improve that results, and this point is one of them. The compression needs to be more needs to be more worked to obtain better results. I don't know if I answer your question.
Sure, yes, that's very good. Thank you.
Thank you.
Okay, thank you very much by your question. Please, there are any question more, the audience? Okay, if not, please, thank you very much, Cruz, about your excellent work and promising work, and continue with success that we all expect. Thank you and congratulations.
Thank you.
Bye. Bye. Okay. Good afternoon, and the next speaker is sorry if my error in your name, Chakraborty, correct? Mr.
Yes.
Chakraborty? Okay, sorry, my
no problem, it's fine.
and congratulations and welcome to the conference. And you will talk about damage detection in 4-point bending tests on behavior, RC, structure, using factor-based fusion. Okay, in very few seconds, please summarize your work and what you would like to salient in terms of your work.
Okay, thank you, and good afternoon, everybody. So, what we did actually, we used embedded sensors such as ultrasonic sensor and also the strain gauge sensors in the concrete structure. And so to detect cracks, we performed the 4-point bending test. And after that, we use the fusion algorithm to combine these both techniques into a single platform for the damage detection.
Okay, you in a general way, in a general context, what is the sensitive that you obtain with your technique in between experimental concepts? Is expectable to use in real cases?
Yes, actually, so we perform this kind of test also in the real structure, such as real bridge. So we have embedded those kind of sensor in the bridge near to Gliwice, Poland. So in there also we have ultrasonic sensor and also the strain gauge sensor. And also I did the same different algorithm to fuse the both techniques and make it into single platform. We have also similar results in there. So it is actually like because for the strain changes or from the ultrasonic sensor also it changes, it detects the changes in the structure. So it is the both similar phenomena. So when we combine using the fusion algorithm, so it gives more accurate result by reducing the false alarm ratio. As example, like from my paper, what I shown, when we use the fusion algorithm, the coefficient is in not goes to the negative values. So when if someone use the like a threshold techniques to detect the undamaged and damaged situation, so in that case they have a more detectability and less false alarm ratio. So that's actually improved the using the fusion algorithms.
Okay, but you say that nowadays it is necessary to compare the sensitivity of this technique in real structures. This is a limitation
No,
because
indeed, because
in the conclusions you say that there are necessity to more studies to compare the sensitivity of this technique on real structures. This is a limitation yet? Is necessary to improve too much for future?
Yeah, in future actually, because now still it is like in the real structure also it is we perform only the load test, but the necessity is like for long-term monitoring. So example like 1 years of monitoring data, and in that case how we can fuse the data and also like combine the both information as a yearly based, means for long-term monitoring cases. So that is still the limitation. So that needs further investigation.
Okay, compared with the 12 techniques that we have nowadays, what is the advantage related with the traditional techniques? What is the benefits that you expect compared with traditional ones?
So example like in there the main sensor, it was a ultrasonic sensor which is embedded inside the structure, the concrete structure, so in the bridges also. So it has a less temperature effects, surface effects than traditional ultrasonic sensors, and also at the same time it has a long durability, so it can stay in the structure and we can monitor the structure continuous basis. So that's a big advantages of using these embedded sensors.
Okay, okay. Please, any questions? There are any questions from the audience that we can expose to the speaker? Okay, if not, thank you very much by your presentation, by your interesting presentation and very promising results that you are obtaining. Thank you very much, and
Thank you very much. Thanks
good
for
luck for your future work. Thank you very much.
Thank you.
Okay. Next speaker is Francisco Leone from Norway.
Hello.
Hello, Francisco. How are you? Good afternoon.
I'm fine.
Please.
Thank you.
So you are talking about high temperature tensile properties of AA6082 filler wire used for solid state joining. Please, in a few seconds, summarize your work and what you would like to give more attention for your work. What is special in your work?
Okay. So the scope of our work was to assess the mechanical properties of this wire that is made of aluminum alloy 6082 at different temperatures. This wire is used in a joining process that is called the hybrid metal extrusion and bonding process that we are developing here in Trondheim. And we are trying now to develop a finite element model of the process in order to optimize it. The main problematic feature of the process is the feeding of the wire into the tool that is the core of the whole joining process. In the past, we have developed a finite element model that gave us quite good results, but we use the material flow stress data available in the deform 3D software that we use for the simulation. But now we are testing the actual material to obtain the actual data for the flow stress with respect to temperature. And so we tested this material up to 500 degrees, and we will use the data that we obtained in order to have a more precise model for the finite element simulations. Yeah, that's.
Okay, in your work, Francesco, do you think that could be that should be take account the effect of the environmental conditions when you are increasing the temperature? For example, there are any phenomena of the oxidations that the environment can contaminate the results, because you are increasing the temperature. Okay, you go to until 550 degrees, correct?
500 degrees. 500.
Yes.
Up to 500. This temperature was chosen because in our process we measured with a thermocouple the temperature inside the chamber that the wire is reached during the process. But since in the tool the wire is extruded and the time that pass inside this chamber is very low, since the process is quite fast, and it involves extrusion that doesn't take so much time. So I don't think that the environment atmosphere would affect in our case the response of the material that is subjected to high deformation, as in our case, since it's extruded quite fast.
In this case, not including the frontier of the grains. No oxidation. Not oxidation. You did observe oxidations between grains.
No, we are not taking into account this in our modeling and our work.
And the viscoelastic behavior, special to the creep behavior, you say that the extrusion is at low conditions. The time is low in the sense that the process is fast, since the okay.
Okay.
Okay. You don't have any additional effects except only the related with the welding process.
Sorry, I haven't.
You don't have additional parameters only related with the process.
We are taking into account of the temperature, and we will take into account of the strain rate. And this, for now, will be enough to model the material during extrusion in our model.
Okay, and between the results between the numerical and experimental are satisfactory.
Yeah, we had a match between we compared temperatures and the slip factor, which is the ratio between the velocity of the wire inside the chamber and the theoretical velocity that the wire would experience in a perfect condition of a sticking condition, and the results are quite in accordance. So we are optimistic in this kind of.
Okay, please. Thank you very much, Francisco. There are audience, please. No questions. Okay. If we don't have any questions, thank you, thank you very much, Francisco. And now I invite Sarah to talk. Please, Sarah, how are you?
Hello.
Hello, Sarah. How are you? Everything okay?
Yes.
Okay. Welcome to the conference, and summarize your work in a few seconds, please. What you'd like to salient from your
My work is basically a review about the PLA-based composites reinforced with continuous carbon fibers.
Okay. Why you select continuous carbon fibers? Because in general, this technique is not so abundant. In general, have some limitations yet. Why you select? You think that there are a lot of work to do in the future to develop this solution for structural integrity?
Yes. Basically, some works are based in change the structure of the head of the printer and avoid some voids in the samples.
You say in your work that you have nowadays several limitations in terms of equipment. You don't have equipment yet, and other ones are related with the parameters to produce these materials. In this moment, there are a lot of work to do. If in terms of 3D printing, if you have a lot work to do, especially in this domain, you have a lot of limitations. In this moment, start with the equipment, correct?
Yes.
Okay, and next step should be to study the parameters. Which parameters you think that is more important in terms of to obtain the best properties?
Maybe
of course, materials are important, but when we are not talking in terms of the materials, we are in terms of the technique to develop these materials.
Printing directions and temperature, maybe. I think that one of the most important.
Okay, this is a work about is a review, a short review about the studies that were developed in this field. Is not too much. The limitations is so vigorous and so abundant that probably you will be a part of solutions, and I wish you best luck to solve all these limitations and results. There are any questions, please, in the audience? Okay, Sarah, if not, if nobody would like to put more questions, thank you very much, and I wish you lucky for your work.
Thank you. Bye.
Your future work. Bye. Thank you very much.
Bye. Thank you.
Okay. Okay. Good afternoon. I will talk with Saltiti. Good afternoon. Hello? Di Maio? Hello?
Hi,
Hello, Di
hello.
Maio. How are you?
How,
Good afternoon.
hi.
Uh,
Sorry. I'm Andrea Pranno because I would like to signal to Prof. Iacovello that there was a typo in the reported author of the Excel file. The speaker
okay,
of this presentation is I'm Andrea Pranno. I'm not Umberto De Maio.
okay, no problem. But we will talk
Okay.
about nonlinear analysis of micro instabilities in fiber reinforced composites, correct?
Yeah. Yes.
Please select your work. Summarize your work in a few seconds in order to.
Okay, the aim of this work is to investigate the failure induced by microscopic stability phenomena in composite materials, because this failure mechanism may lead to a notable decrease of the composite compressive strength. A detailed microscopic continuum analysis with an appropriate representation of the different sources of nonlinearities is usually required to capture the effect of the different microscopic failure modes, such as instability or fracture damage. In order to avoid a direct modeling of all microstructural details of the composite solids that is computationally expensive, a semi-concurrent multiscale approach has been proposed in which the macroscopic constitutive law is evaluated, resolving a micromechanical boundary value problem in each microelement of the homogenized domain. Some numerical results are obtained to provide an accurate prediction of the critical load level associated to the microscopic stability in two-dimensional fiber-reinforced composite solids. And we noticed that the proposed semi-concurrent multiscale approach is effective, but the results are a little bit influenced by the boundary layer effects given by the external constraints.
Okay, thank you by your short abstract of your work. My question is, what is new in your work related with the state of art? What you would like to improve?
Yeah, the problem
if you
is
can
that,
summarize the benefits with your work, what you are improving related with the state of art?
Okay, the problem is that the interaction between the stability and other type of damage process like the microfracture in composite materials is difficult to implement in a numerical model because is computationally too expensive. We are proposing a multi-scale model able to reduce the cost of this simulation, and in the literature there aren't a lot of multi-scale model that allow us to define the best multi-scale model able to reduce the computational effort and capture the interaction between contact that we have in micro cracks and microscopic instability in such type of composite materials. So the main contribution for us is to reduce the computational effort of such simulations. And the problem is that the multi-scale model that we have proposed is efficient, but we need a good parallelization of the numerical procedure, because every microscopic boundary value problem should be computed by a single core of our processor of the computer. And if you don't have a good parallelization of the numerical procedure, this method is slow. So we are working on other kind of multi-scale approach, that is an hybrid multi-scale approach, according to which hierarchical approach is used to obtain a nonlinear macroscopic law away from the critical regions, and we want to keep a detailed microscopic modeling in the region affected by macroscopic stability phenomena. The main advantages of such approach is the high computational efficiency. We don't need a periodicity and scale separation assumption in region undergoing damage, and the strain localization and the boundary layer effects can be be analyzed in a unified manner, but this work is still in work in progress, and we don't have still analyzed the interaction between instability and microfracture, but we have analyzed only the microscopic stability. So it's still a work in progress.
Okay, but basically, what is the main limitation of your formulation?
The main limitation is that we have a strong influence of the boundary layer effects, and if we have a concentration of the external load, or if the external constraints are effective on the model, the results are really influenced a lot. So we need to change this model and improve this formulation to avoid these boundary layer effects. But in terms of critical load factor, we obtained a good result, because we obtain a percentage error of about 1% respect to direct numerical simulation. That is computationally huge. That is computationally expensive.
Okay, thank you very much by your interesting talk. Questions, please.
Thank
there
you.
are any questions from the audience? Okay, if not, I wish the best for your work.
Thank you.
And continue with your progress. Is welcoming and nice to see you again.
Bye. Thank you.
Fast. Bye. Thank you very much. Bye. Okay. Good afternoon. Salfiti.
Yes. Hi to everyone.
Hello. How are you? Good afternoon.
Fine.
Welcome. And thank you by your interesting talk that is about mechanical properties of flexible graphite.
Yes.
A review. What you, in a very short time, what you have to summarize of your work is a review, but in general, what you can.
I found some information about this material, which is flexible graphite, and I compared the data. Basically, flexible graphite is not that common for structural purposes, but it's mainly used in electrical applications. For example, in thermal cooling of microchips, or as an electrodes in fuel cells. But probably the main mechanical purposes in which it is applied is as insulator for vibration. For example, even in sealing and gasketing application. And I found some data about mechanical testing, and especially about the effect of density on tensile and compressive properties, and even about viscoelasticity. The main focus of such review is about tensile properties, compressive properties, and viscoelastic properties. Yes, there are not so many data about purely mechanical properties such stiffness and strength of this material. But it's very interesting because of its coefficient of thermal expansion, which is very low, so it can be applied. It should be studied a little bit more to be applied in more specific mechanical applications. That's why I made such review.
In terms of applications, industrial applications, what you think? There are not in terms of electrical applications, because you said that is normal. Is more limited in mechanical, in structural applications. What you think is limited yet, or is a limited material? There are limited knowledge.
There is a limited knowledge about it. It can be, for example, in the last year, the piezo-resistive behavior has been studied, So it's basically like a mix of mechanical and electrical. It's for a mix of mechanical and electrical applications. So that's very interesting. And it is anisotropy, so it's common to find it in foils, very thick foils and very flat. For example, it is anisotropic even from a conductive point of view, and from even the strength in compressive direction is different in plane and out of plane. So a lot of properties has to be studied more. There are no information about tensile strength at high temperature or compressive strength or fracture behavior. There is I didn't find anything about it in literature, neither in fatigue, for example. But yes, the basic stuff, basic properties are not present. I mean, there are not that many data to have a proper characterization of such materials from this mechanical point of view.
Okay, there are work to do. There are a lot of work.
Yeah, there is a lot of work to do.
But in general, this material promise.
Yeah, I believe so. And that's why I'm keep continuing to study it. And yes.
Okay, Salfiti, congratulations. Good luck for your future work, and I hope to in the next event to have news about the work that you are developing, because it's very exciting, the topic. Thank you very much. There are any questions from the audience, please? Okay, thank you very much. Okay, thank you very much and welcome. See you soon. Bye.
Bye.
Okay, next talk is from Fatima. Fatima, are you there?
Here, Mohammed is a co-author in the paper.
Okay, he's a co-author. Okay, welcome, no problem. Thank you, and welcome to the first virtual conference in structural integrity. Nice to have here and with an interesting talk about maintainability and reliability of high-density polyethylene pipes through experimental and theoretical models. Please, can you summarize what you?
Yeah, I'll give a summary of what we've done in this work. It's really the ultimate result of what we're doing since 5 years now. It's about dealing with HDPE pipes as a liner, as a coating, and as a pipe itself. And we are trying to study the damage models and the reliability behavior, and to decide if we'll do which strategy of maintenance we'll have to deal with while having a problem with with the pipes or with a liner. For example, we have in Morocco some big pipes with phosphate, for example, which have a liner, an HDPE liner inside, and when the liner have a problem, for example, a fracture or a damage. So we have to decide when to do the maintenance for that liner, to take it out and to replace it. So for our work, we are working over many models. We are all working with experimental parameters like the pressure and the strain, the stress, and the energy. And from that, so we are doing two kind of tests. We are doing burst tests of pipelines, and we are doing also tensile tests. Those tests give us the parameters, and those parameters have been used to establish the models and to find out the correlation. So now we have an energy model, we have pressure models, and we have models based on the unified theory of Peacock. So we have modified the theory, and we've introduced the pressure as a parameter in those models. We've developed all the maintenance strategy to develop to maintain the HDPE pipes, and to decide when to take out the HDPE liners or the HDPE pipe from the piping network, and to replace it or to repair it. So our work is what we are presenting here is a general idea of all what we've done till now, and we've focused over one point, which is the reliability and maintainability. So if we can maintain or not, so we are focusing about the critical life fraction, which is the beta C in our paper. So when, for example, when we reach 52% of the depth of the damage in the liner, if the liner, for example, is we have a notch of 52%. At that time, we decide that over the 52%, the damage become brittle, and the pipes can break down easily, and the behavior becomes you can't decide 100% that the pipe will have a previsible behavior. So the critical life fraction have been defined, and this life fraction give us the opportunity to assess the maintainability model, which is when to at 52% we've also established laptop curves. So in the laptop curves, we've find that beyond 52%, the pipe must be changed or rebuild. So we can take apart and do the welding for a part of the pipeline.
Okay, you have theoretical models.
So for the theoretical models, okay,
but
go ahead.
The theoretical models that you have, there are good correlation related with the experimental ones.
Yeah, they are at 95% reproducing the experimental models. So they are originally based on experimental parameters. So in the strain elongation curves, we've defined two parameters, which is the maximal pressure at the necking of the limit of the elastic phase, and another pressure at the rupture phase. So those two pressures have been used as an alpha model, and with them we've modified the Fopel formula, which is estimating the burst pressure of a pipeline. And but the Fopel formula is usually used for steel pipelines, for metal pipelines, not for thermoplastic pipelines. So our model is based over modifying one part of this is modifying that formula, putting an alpha coefficient, and having a new model using this. And we've established also one pressure formula related to the, you find that in the presentation, related to the critical life, to the life fraction, and it's two equations. It's written two equations according to the interval of the life fraction, and the life fraction it's the variation of the depth over the initial depth. So we can see that the formula leads us to define one continuum model using that life fraction and other parameters deduced from the experimental curves.
Do you think that could be applied to industrial applications, for real applications?
Yeah, we've applied that in one application, pipeline network, and the people now in one distribution in the city we are in, they are taking that in serious, and we've confirmed with them that when we have a damage till 52% of the notch of the damage of fracture in the pipeline, they take it out because when if deleted, it's a leakage after. And our work is one interesting thing about our work is that we are studying the fatigue phenomena of pipelines, but replacing it with two things. It's like we are creating notches like a preloading. After that, we are doing tensile tests of the specimens. So and we are using the unified theory to we are using in the factory to establish the damage models and to predict the maintenance strategy choice after that.
Okay, thank you very much. There are any questions, please, from the audience? There are any particular question from our colleague? Okay, if not, the time is flying. This is a problem because the talks, the speakers suggest very interesting talks, subjects, and the time fly, and we don't have a lot of time to explore in more detail. Thank you very much for your exciting work that you are developing, and I wish the best to continue in your work. Thank you very much. Bye. Bye. Okay, I will ask to Souza.
Hello.
Hello, Souza. How are you? Good afternoon. Welcome to first virtual conference in integral structurality. You will talk about outline displacement analysis of rotating blends using digital image correlation. Okay? Congratulations by your exciting work, and please summarize very fast your work, what you would like to give emphasis in your work.
Okay, so we started with an RC helicopter, and we wanted to measure the displacement of the blades that it suffers when it's moving, when the blades are rotating. And we developed a method to do that using digital image correlation. We developed a system to trigger the cameras to illuminate the specimen and perform all the control necessary to obtain images that we can analyze and obtain results. Then we made a computational model, CFD and EFA fluid structure interaction model, and we compared the results and we obtained agreeing results between them. I think very fast is this.
Okay, thank you very much. In fact, what is the real applications that your work can be used? You said helicopters, you've said blades, but in fact, in which circumstances, in which real applications you can use the technique that you are developing?
We can use it not just in helicopters, but also in wind turbines, for example. We can use it to validate models, computational models. That's what we did in this work. We validated a computational model and validated them both, the measurement and the model. And we can also use it to analyze the way that the system is working and find issues with it. We can find, for example, in the RC helicopter, before we made some changes to it, we could notice perfectly the instability of the rotation axis.
Okay, basically, what is the limitation that you have in this moment for your work?
Biggest limitation in this kind of very fast image acquisitions is always lighting. We have to have a huge amount of light. That's always the limitation for this. Usually, above anything else, it's light.
Okay, thank you very much. There are any questions from the audience? Okay, if not, Souza, thank you very much for your work. Sorry, but we are a little bit delayed, and we will go for the next speaker. Thank you, Souza, one more time. And next speaker is Eslami, System Design and Development of Friction Stir Welding of Polymers. Okay, thank you very much for your interesting work, and special for me. And I have and I have here one question special for you because it's
Okay.
very interesting your work for me. Please summarize your work
So
very fastly and what you
basically, the
should
thing.
go emphasis in your work.
Okay, basically, we started to see the possibility of welding polymer with FSW, and the main focus was developing a tool, which we did because the main welding tool that is available, it's required external heating source and complicated control system. So we could achieve very good result in the laboratory environment, and the main achievement was to obtain the tool, and also we made a force platform to be able to record and somehow make the actual force as a welding parameter, even using the position control welding method. I think that was the fast method, but if you have a question, I would happily answer.
Okay, please. You can say that in this moment you have the design of the tool. You have the best parameters to welding the polymers.
Yes,
And
but
in terms of performance, mechanical performance, your welding solution is competitive related with the properties of the material of the derived materials. You can have, or by other words, when you weld to polymers, basically the failure occurs in the welding joint or in outside in the adherent.
We studied two different configurations. The first one was the dissimilar polymer and the lap joint. When it was dissimilar, it's usually because we had dissimilar polymer with a dissimilar thickness, and most likely the thinner one broke, but not from the weld magnet, but from the heat affected zone. In the lap joint, we could achieve around 76% of the tensile shear strength of the highest performing material. But then we improved the tool, and we again optimized the parameter for the similar polyethylene, and with those we could achieve 97% of the tensile strength. So for us, even in the literature, you cannot find as good as those results, especially with the fusion welding. So the results are very promising. However, the main limitation is we just work in the laboratory environment. So we have to study for the longer term and longer weld line if it needs to be industrial application.
Okay, and next step could be composite materials. What you are expecting in terms of composites? When we are talking in terms of composites, we have short fibers or long fibers, continuous fibers. The mechanical performance are totally different. You think that you can go to values very close of the mechanical properties in terms of continuous fibers, composites with continuous fibers?
Well, continuous fiber, as you know, if we penetrate into the material, we would break the fibers. That there is no doubt. We have another solution which called the lap welding, which we don't penetrate the pin, so we just have the like a shoulder above the material, heat it up, and then forging together. But this lap welding doesn't create very strong welds because you don't have the stirring effect of material. So in my opinion, if you have enough resin, thermoplastic resin, and if you can mix it, I think we would at least, even if it breaks the fiber, it might have a good result compared to other techniques. So for us, we know we are changing the properties of the material and we're breaking the fiber, but if we can produce even the joints better than the available techniques, I think that would be a progress. But with the short fiber, now we are studying, and I think short fiber for sure is much easier because there is no, we don't break the fibers, it's just mixed.
Okay.
We prefer now we are doing, yes.
Thank you very much for your very interesting work, special for me, because I am very excited with your work and with your results. And probably in future we will talk about this, but in this moment, sorry, we will finish here because the time fly. And thank you very much by your talk, and good luck for your work. Please, Barros. Hello, Barros. How are you?
Hello, good afternoon.
Hello, good afternoon. Welcome for your first virtual conference on integral structure. Please, your talk about background features has a reference system for camera calibration in design image correlation. Please summarize and give your emphasis of your work for us very fastly.
Thank you. So this is related to digital image correlation and using random fixed objects that are detected by feature detection and matching algorithms to keep cameras calibrated in field measurements. So it actually talks about two different procedures that we developed. One of them is related to compensating the movement of cameras, either when they stay in the same place and move, or if we need to take them away and return at a later time. This is for field measurements in structural monitoring. So it's good to be able to take cameras away and take them back without losing our calibration parameters. And the other procedure we developed is for the monitoring of structures using one camera mounted on a drone and then using background features to be able to take a displacement field from a DIC method, but using random objects detected and matched throughout several images in order to know the camera calibration so that we can get a 3D displacement field.
Okay, you are talking in terms of mechanical and electrical conductivity, correct? No, sorry. I change. Sorry, my question. Can you frame your work for real applications?
Okay.
Where you can use, where you can apply your work in real contexts?
So this is thought for structural applications. So for instance, if we want to monitor something long term, if there's a structure like, for instance, a wall that we want to know how it moved throughout a number of years, we cannot, for instance, have a system there for all those years operating without moving and keeping it stable. So this would help to go there, get a measurement, and the next measurement we need is a year after that, so we can go back after a year and get consistent results. And with the application with the drone would be to be able to get to inaccessible places. For instance, we've done digital image correlation measurements on a bridge, for instance, and we're actually fortunate to be able to find a good place on the ground to place a camera, but that's not always possible. So if we could take a drone there and be able to calibrate the camera and obtain 3D measurements, that's very advantageous in cases of inaccessibility, for instance.
Okay. The next question should be what is the advantage? But I think that you just said what is the benefits of your technique compared with the traditional ones that we are using now. Okay. Barros, thank you very much. Sorry, the time is flying, and congratulations by your excellent work, and I hope to have news about your future works and improvements. Thank you very much, and sorry. Bye.
Thank you very much.
Okay. Next speaker. That we will talk about analysis of experimental behavior of structural functional carbon fiber reinforced plastics under bending. Hello? Singh? Hello? He's not here. Think. Okay, we'll go to the next talk. High strain rate behavior of Alclad AA 2024 T3 aluminum alloy bar using split application tension bar from Paulo. Hello, Paulo.
Hello.
Hello, good afternoon. Please, can you summarize your work
Sure.
and give emphasis what you are doing now?
Sure. Our work is about the strain rate characterization of Clotted 2024 aluminum alloy. We are using split Hopkinson bar method device, as you mentioned it, and we are also included the temperature effect on our dynamic tests. So basically, the material is 2000 series material. It's really a popular material in aeronautics, small aircrafts, and medium haul airliners such as Boeing 737 or Airbus A320. And there is a need for a dynamic database in case of any foreign object damages or any tool drop during the maintenance and so on. So in the literature, there are studies about the 2024, but not much study on the Alclad 2024. The studies are mostly related to the fatigue life behavior of this material or the effects of friction steel welded joints or riveted joints, but not in depth about the temperature and the strain rate effects of this material. So we designed our heating chamber for dynamic tests and also our Hopkinson bar. So yeah, the goal of the work is to characterize this material. Yeah.
Okay.
And of course,
about two questions. I have two questions for you. For example, the first one is about the temperature effects that you in your test you are increasing the temperature, but during the impact you have more temperatures. How combine these two types of temperature? Sorry, in fact. There are no two types, but you understand my questions. You have temperatures from two different conditions, room temperature and the impact behavior.
Yeah. Allow me to explain. There are actually two sides of this study. One is actually all experiments performed in room temperature. So we had this static results and also dynamic effects. So in the dynamic results, we see negative strain rate sensitivity. What was that normally aluminum alloys are not strain rate sensitive, and in our case, we saw that by increasing the strain rate, we actually saw a reduction in the flow stress value. So we tried to find out what's the reason behind it. So we use the thermography and we measure the adiabatic temperature rise of this material subjected to strain rate of 520. And that was one aspect of the temperature that you mentioned, which causes softening and prevents the stress distribution along the necking region of the specimen. And the other aspect of the temperature was the temperature itself. So we actually put the specimens in the chamber, heating chamber. I believe it's in this slide. Designed the chamber for Hopkinson bar up to 250, and the other one was the environmental chamber we performed for the static tests. So that was another temperature-related issue. Yeah.
And what is the effect of these temperatures in the final mechanical properties, in the final performance? There are strong effects when you increase the temperature, the room temperature. This temperature with the temperature, the change is significant. For example, there are a limit where at the environmental temperature don't have effect when it's combined with the temperature promoted by the impact or not.
Well, I can explain it this way. Let's say in our static results, as I told you about the negative strain rate sensitivity that we observed. So the value was around 458 megapascal versus at high rates was around 432. It's around 5% reduction in the strength value. But if you go to the temperature of 200 degrees, if you compare the same temperature in static and dynamic ones, we see actually that there's a change in there. So actually now it's the strength value for the static results are around 366 and the dynamic ones around 409. So it's not low, it's actually higher now. So that's something I noticed during the experiments. But nonetheless, the focus of the thermography and the results were around the room temperature. So we use thermography mainly to see the extra temperature rise, which was around 44 degree. Had affected the plasticity, the plastic behavior of the material.
Okay, your work is very interesting. We can stay here all afternoon talking about it because it's very interesting, but we are limited by the time. Thank you very much. There are any questions from the audience, please? Okay, if not, Sank is not here also. I think that we can close the session. Thank you very much by all participants, and I would like to present in particular and in name of the ESIS the congratulations and thank you very much by your participation and collaboration in this first event that we hope to continue and disseminate this the structural integrity. Thank you very much, and sorry, Francesco. Thank you very much.
Thank you so much, Paulo. Thank you for this really interesting session.